My name is Gerardo Caja. I'm from the University Autonoma of Barcelona in Spain, and I'm going to talk about sensors for sentient small ruminants, and I would like to thank the Spanish Society of Sheep and Goat Production for this invitation. Briefly, my presentation will follow this syllabus, starting with the concept of small ruminants as sentient beings. I will discuss the fact of small ruminants being the last in the list for welfare assessment, but the first for electronic identification. And with this regard, I will compare the current situation of a small ruminant population and that of the communication technologies. Next, I will go into the differences and features of transponders and sensors, and I will present which are the animal-based sensors which are available, taking into account this wearable and non-wearable classification. And we will be deeper analyzing some cases studies. Finally, I will try to give answer to the question if small ruminant sensors are able for an early alert welfare system development on farm conditions, and I will present some of the current results obtained in a project, a European project on small ruminant sensors. And finally, we will conclude. First of all, with regard to the small ruminant welfare frame, we need to clarify if small ruminants have rights and freedoms, or are these only human attributes. The reason of this is the controversy between ownership and freedom, which motivates that currently the known 5 freedoms are named as 5 dominions. On the other hand, there is a full agreement that animals are sentient beings. And although there is not a full agreement on the Declaration of Animal Rights, there is an agreement on the Universal Declaration on Animal Welfare, which is a non-governmental organization aiming to prevent the cruelty, to reduce suffering, and to promote the standards of animal welfare that was recognized by the World Organization for Animal Health. And we consider, and there is an agreement, that humans are responsible for animal welfare. With regard to the small ruminant current situation, they are the greatest livestock population in the world, when poultry is excluded, with approximately 2,300 million head. They are located on areas of poor resources and facilities, but rich in biodiversity. They are a key resource for employment, a capital for many people in rural areas, and their products are favorably considered by consumers. On the other hand, farm size increased during the last years to compensate the rise of cost and profits decline. Moreover, they are fully electronically identified in the European Union and United Kingdom as a consequence of the measures taken after the BSE crisis and the regulation of the European Union on sheep and goat identification, which is very important for PLF, precision livestock farming implementation. But despite this, there is a low Internet of Things penetration in general in livestock, and especially in small ruminants. To illustrate the facts of a small ruminant population in the world, I'm using the maps from wall mapper, showing clearly that sheep is mainly produced in Asia and Africa, with small contributions of the rest of the world. The tendency is more extreme in goats, basically produced in Asia and Africa. But one question rises to me, which is who is interested in innovative developments for small ruminants in these countries? But if we observe the maps of communication technologies, referring to internet use and mobile subscriptions, you can see that Asia is predominant in the use of internet, but when we go to mobile subscriptions, the situation is widely spread across the world, and probably indicating that this technology will develop a key role in the future, and why not related with the small ruminant sensing technologies. Many new technologies are used in radio frequency for communication. This is the reason I put here a chart with the radio frequency bands and their safety risk. The position of the visible light is around the 4 to 8 petahertz, and I'm also indicating the position of the low frequency used for animal identification, which is between 30 and 300 kilohertz, the high frequency used by industrial tagging between 3 and 30 megahertz, and the ultra high frequency also used by industrial tagging between 300 megahertz to 3 gigahertz, which is also currently proposed to be used in some animal sensing devices. And also I am stressing here this is the same position of the Wi-Fi communication devices. In general, the World Health Organization concluded that there is not convincing evidence that the weak radio frequency signals from this base station and wireless networks cause any adverse health effects in humans. But there is a concern in any case, because as demonstrated by BAS in 2009, 900 megahertz applied during the pregnancy duration of rats produce alterations in the hippocampus of embryo brains, which is really a concern. With regard to the differences between transponders and sensors, a transponder, which is a transmitter responder, and is so named microchip, is an electronic device which uses radio frequency for sending a fixed response, which is exactly the electronic identification code. The process is described in the drawing, and the result is a digital signal which is used for processing. The typology of the transponders might be different, and this modify the performance and the readability. First of all is the size. The greater, the better, but this is a limit in some cases according to the weight. The second aspect is the power source. We classify as passive or active depending on if they have or not battery. And also it's important to say that the active need to replace the battery or to recharge, which limit the possibilities of application, for example, in injectables. There is also differences between bands, and we classify according to early mentioned in low, high, and ultra-high frequencies, which are standardized in 134.2 kilohertz for animal identification, with a collision attribute which made impossible to read at the same time two transponders. The high frequency used by the industry for industrial tagging, 13.56 megahertz, which are usually print and they are very cheap. And the ultra high with a frequency around 900 megahertz with possibility of simultaneous reading, but with the concern of safety. And finally, they can vary in the operation mode or the technology, and we distinguish between full duplex and half duplex depending on the ways of transmission. And it should be stressed that all of them are difficult to be read with the same reader. That means in most of the cases, an ISO reader reading different technologies means that there are many readers operating in the same reader. Rapidly, in practice, considering the electronic identification system as a whole, we need several elements like the transponder, the transceiver, the signal processor, and the data user, that in the case of a flock electronically identified, in which one sheep might be identified with one ear tag or with one rumen bolus or one inject in the passer. We also need a transceiver and one processor integrated in the radio frequency unit, which will use the antenna to send a radio frequency wave to the transponders, and the transponder will respond with the code, which will be processed in the processor and finally sent to the data user. Which is also important is that this technology allows reading the animals with no visual contact, which in some cases is really key. On the other hand, which is a sensor? A sensor, also named as transducer, is an input device which produces an output, we call the output signal, according to the input quantity. This input might be physical, chemical, or biological. And it's also to stress that they are part of our recording or control system. They are classified according to different criteria, but I'm using the taxonomy of the National Research Council, classifying as self-generating sensors, in which the response is direct, for example, a thermistor, modulating sensors, which are able to vary the output according to a second input, for example, a fiber optic magnetic field or a laser receiver, and smart sensors, in which the complexity is concealed by an interface and on-chip signal. For example, this is the case of temperature controllers, which are making more than one function. They can be also classified according to the aim, and there are 12 main types according to the technology used. For example, if they are using infrared, or if they are using electronic images, etc., etc. And also, they can be classified as depending on the animal base, and we say wearables or non-wearables. I will use this classification in my presentation. So, considering the animal-based sensors and the wearable category, which are placed on or inside the animal, I'm presenting here a table in which we have the type, the technology, the indicator, the device, and the use. You can go later in detail, but The transponder, for example, which is not exactly a sensor, is used for sorting animals in arrays or feeding or mating controls. The the GPS are used for virtual fencing, spatial location, grazing monitoring, behavior monitoring, etc. And also, as you can see here, for the mother-offspring relationship. We have also more specific devices like temperature, pH, pressure, sound, acceleration of biomarker sensors with different uses, like, for example, detecting fever or stress or heat for mating, drinking bouts, the feeding and rumen function, the rumination, heart rate, coughing, the animal motion, resting, feeding, rumination, all the main aspects related with behavior, lameness, and also the detection of the amount of metabolites. The second group is the non-wearable, which are usually mounted in the facilities, like, for example, those based on cameras with optical image, infrared image, near infrared, 3-dimension or lasers. And the use is normally for studying behavior, calculating growth, general supervision, behavior in general monitoring, thermometric measuring, udder health, for example, to detect mastitis, head and hoof health, and animal stress, for example, reading the infrared image of the eyes. The near infrared is used commonly for estimating milk flow and is used for milk volume and also can be used for milk composition. 3-dimension imaging, which is used for body condition score and estimating body reserves. And finally, the size and growth can be estimated using laser beams. But we can use microphones or weighing cells or ambient sensors. For example, the microphones for detecting coughing and analyzing which type of coughing is affecting the animals. It can be also used for alerting lambing and detecting acute stress. The weighing cells for growth and weight, for gait recording and estimating lameness, as well as the ambient sensors for the comfort of the animals and health monitoring inside of shelters. You can have a complete detail of all these aspects in the paper that I'm attaching the link, what was published the last year. All these animal-based sensors might be installed on a sensor system under on-farm conditions. This animal is providing the inputs to the sensor and the output is producing the signals, which are usually sent using radio frequency and produce results from which we want to obtain advices. But in most cases, we can use also existing complementary data. For example, the previous animal performance, health and behavior data, or environmental data, or non-sensor data, as, for example, economic information, and also we can filter them according to limits. But the question is still, which is how we can produce advices from the signals. For this, we need to make a labeling process in which we characterize the animal response. We fed with this response to a mathematical system to produce a detection algorithm, and also we compare our signals with a gold standard, and according to that we fed also the algorithm, and we elaborate with all the complementary data a decision model which arrives to produce results and the final advice. As examples, I'm bringing here some case studies relating the use of the sensors for small ruminant farms. The first case is a smart monitoring and alert system for electric fences, which is measuring the fence voltage every 10 minutes and alerting immediately on fence problems. The system have a transmission system and also a GPS, and is self-sufficient to operate by using solar panel and lithium batteries. Probably one of the most interesting applications of GPS for small ruminant farms is virtual fencing. In this case, the device is mounted in a collar containing a GPS sensor, a Bluetooth unit, and also the batteries. The farmer draws a map of the grazing area, and the systems prepare a warning zone in which, if the animal goes out the grazing zone, is averted by a sound increasing in frequency, after which receives an electric shock. It looks like sheep are inefficient learning this device, and the currently available devices are unable to keep sheep within the borders, and it looks that it's necessary more research, and also it's important that there is an ethical concern, and in some countries the system is not allowed. Another interesting application of sensors is the use for meal recording. In this case, the animals previously identified with transponders in ear tags or in bolus are read through a tunnel reader, and maintaining a fixed order of entrance in the milking parlor. The milk flow meters collect the milk flow, and by using the time of milking, the milk yield is calculated. In general, the reading efficiency varies between 96 and 99%, which means that in cases of animals not detected, it will produce a line error, and it's necessary to introduce the ID of the animals by hand. Regarding the cost of the technology, here I'm presenting a study in which it was calculated the break-even point of using electronic identification for performance recording in sheep, depending on the productive aim, the reader price, and the electronic identification device price. According to this study, in which the reader price was 600 euros, the full investment were paid depending on the productive aim of the flock, but on average we can say that the investments were fully paid for the savings in performance recording of the flocks between 400 and 1,200 euros. Currently, using the same data of the study, at the prices currently in the market of some readers, the break-even point decreased dramatically, and it was paid the investments with values of 400 or 200 EUs. Another interesting device using sensor is the so-named walk-over weighing device, in which the animals are attracted to pass through a weighing scale because they have a water point or a salt or concentrate feeder, and automatically recorded their weight. The current cost of the device is approximately 5,000 euros, and it's cost effective in some farms currently in Australia. Similar sensors for weight are used in a lameness detector developed to detect the lameness in extensive flocks. The device is weighing separately the hoof load of each leg, and when applied in a flock with a lameness prevalence varying during the study between 10 and 33%, it was stated that the healthy hooves show a greater hoof load in the front with regard to the back hooves. It was also stated that extensively infected hooves have the same load. The sensitivity and the specificity were enough to make this device interesting for using in practice. On the other hand, when wearable devices are studied, it's very important to determine which is the more effective body side to be attached. In this case, the behavior of grazing sheep was studied as presented in this drawing, and attaching the same type of devices, which were accelerometers, in one ear tag, in a collar, or in a leg. And the behavior patterns studied were grazing, standing, walking, or laying, some of them including rumination. The effectivity of the position to determine the behavior was greater in the ear compared with the other positions. In some cases, the device need to be placed directly inside of the animal, such as the device that I'm presenting here, prototype developed in the last years in the Universidad Autonoma to measure rumen temperature in dairy sheep. In this case, we compared the thermoneutral and heat stress conditions, and as you can see here, the rumen temperature varies dramatically according to the ambient temperature, indicating that rumen function was different in thermoneutral and heat-stressed animals. To give answer to the question if sensor can be used for the purpose of welfare assessment, it's important to remember that the Welfare Quality Project re-elaborated the concept of 5 freedoms and defined 4 main welfare principles that split into 12 key independent and optimized welfare criteria. In 2015, a following project, the Animal Welfare Indicator Project, studied the welfare of small ruminants and proposed several assessment protocols for extensive sheep, meat purpose, and intensive dairy goats. No protocols were proposed at the time for intensive sheep, for fattening lambs, or dairy sheep. And currently, there is animal welfare developed in Spain by Interovic for sheep welfare assessment for lamb and kids fattening farms. You can, with the link, access to the protocol. The 4 welfare principles of the AWIN assessment project are widely known and correspond to good feeding, good housing, appropriate behavior, and good health. These 4 principles are also divided in 12 welfare criteria and also split in 24 welfare indicators. When the AWIN 2 steps protocol was applied in Italy in 30 dairy goat farms, the main problems detected were low body condition score, fecal soiling, dirty hind quarters, dirty legs, head lesions, mainly the horning problems and broken ears, claw disorders, and knee calluses. That means that these are the basic area to look for the objective assessment by using sensors. When the same welfare assessment protocol was applied in different conditions, in this case in Spain using Florida dairy goats, the results varied dramatically in some aspects. Especially, you can see here the hair condition, the horning defects, and especially the human contact. Similarly, when more welfare indicators were considered, they arrived at the same conclusion. They are coincidences, but they are also differences depending on the breed and production conditions. And in conclusion, they are no full coincidence, needing more research. And these are one of the first aims of the Take Care project, part of the H2020 program of the European Union, in which we are trying to prioritize the small ruminant problems in Spain, as well as in other countries, with regard to the production system. In the current studies done, the first priority aspect in meat sheep were nutrition. The second was shelter and facilities conditions, and the third, the density in intensive conditions and stocking rate under extensive conditions. With regard to dairy sheep, the main problem detected was mastitis and milking management, followed by nutrition and the shelter conditions in basically under intensive production systems. And when with regard to goats, the situation was very similar to dairy sheep: mastitis, nutrition, and shelter conditions. Regarding lambs and kids, first corresponding to milk-fed lambs and kids between 0 and 2 months of age, the most important problem detected was related with colostrum and periparturation, basically management and quality. The second was hygiene and disinfection of the shelter, as well as, in the third place, the shelter ambient conditions and the hygiene of milk feeding facilities. In the case of fattening lambs in Spain, after weaning and between 1 and 3 months of age, the shelter facilities conditions, that means the ambient conditions of the shelter, was the first. The second was animal density and bedding conditions. The third was related with respiratory diseases and problems. And the fourth, hygiene and disinfection of the shelter and the facilities. In a second step of the project, we asked to experts and farmers which was their opinion about which technology or which sensors will be more useful for detecting the welfare problems. And the answers indicate that weather station with internal and external sensors will be the first choice. The second was an automatic scale with drafting. The third, the use of high-frequency ear tags and readers. And finally, a 3-axis accelerometer plus GPS. Here you can see one of these proposed weather station with different sensors to be used internally and externally in the farm. With regard to dairy sheep, the response were the first option similar, the second corresponded to an automatic meal meter, the third the automatic scale for weighing the animals, and the last a 3-axis accelerometer. In the case of dairy goats, the weather station was also the first option, followed by automatic meal meter, high-frequency ear tags and reader, and 3-axis accelerometer plus GPS. And finally, for lambs and kids, weather station was the first option, automatic scales for automatic weighing of the lambs, automatic feed intake monitoring, and air ammonia meter in the shelter were the other options proposed. Going to finish, I'm proposing some conclusions of my presentation. The first of all is consider humans as responsible for animal care and also the real need for welfare assessment protocols. Second, the small ruminant should be considered as a huge market for sensor development and PLF implementation. With this purpose, the generalization of electronic identification in a small ruminant is a key for individual welfare assessment, and this, in the case of the European Union, might be an strategic advantage. Reviewing the concept of sensors, they are electronic devices, but they are input devices producing variable outputs, we call that signals, according to the input quantity. And we are expecting many new developments in a new future. Between them, wearable sensors seem to be the ideal option for early alert or warning systems, and also non-wearable might be the currently cost-efficient option for small ruminant welfare assessment and also the early alert warning systems. According to the results of the Tech Care project, the current prioritization of welfare problems seems to depend on the species, the age, and the production system. And finally, not all sensor device expectancies are today warranted for small ruminants. And with this in mind, we need further applied research and the collaboration of innovation companies for the new developments. And I want to conclude with some acknowledgements. First, to the European Commission, H2020 Research and Innovation Program for the grant to the Tech Care project, to the International Tech Care Consortium and to our coordinator Claire Morgan Davis, and also to my colleagues in the Spanish Tech Care team, basically those of my university in the Department of Animal and Food Science, in the Department of Microelectronics and Electronic Systems, as well as to those involved in the farm side, which are González from Gestión Empresarial de Ovino and the group cooperative of Pastores Ovi Aragón in Zaragoza. This is all. Thanks for your attention, and a last reflection about which will be the black sheep in the flocks. Thank you very much, and I'm able to accept questions.